load lock should be under vacuum. So we're just gonna run the LL vent recipe to, well, you know, vent the load lock. We have an 8-inch carrier wafer. Whatever sample you have, you're just gonna tape onto the carrier wafer with capped on tape. You can use double-sided if you don't wanna have the tape on top of your sample. Carrier wafer goes face down in this ring here, and then this ring just sits on this port in the load lock. So it's going to be a bit sensitive. If you use, let's say, aluminum instead of steel, would that work?
We're looking to use steel just so we can make magnetic fixtures to put inside the E-Beam.
So what are you planning to, what are you depositing on?
We're depositing on silicon, but we're just looking to use like fire tube fixtures instead of just using Teflon tape. Like we'll CNC something from aluminum, put the wafer inside a little bit, and then just like
Yeah, I kind of get what you're saying. So, short of it is like, I'd weigh the 8-inch carrier, just an 8-inch silicon wafer, and then just sort of see. So you want to use steel because you need something with magnetic attraction. So it is going to be weight sensitive. Like, this fork is going to extend out about 18 inches. There's going to be a little bit of leeway, like it doesn't have to be perfect, but we sort of just have to see, which also means that it is possible that you make, or you bring it that steel mask and then we find out that it's not going to work. Anyways, we can talk more in a second.
Yeah,
so
sure.
I'm going to shut the load lock, and then next step we have to do, we just have to pump it down. That is going to be done with the LL pump recipe. So when you press LL pump, it's going to bring up this, I don't know, intermediate screen. Your options are cancel or continue, so we're going to hit continue. Okay, so this is going to take about 5 minutes. So is the steel, is it a mask?
replacing plate and everything else.
So replacing the carrier wafer?
Yeah. It'll just be like a steel plate from like Jim Hudson or something like that. And that was like 6 inches.
Eight.
Right on the steel fabricator.
Okay. How big are your substrates?
Well, it's not the size of the substrate, it's just like the quantity of the substrate.
Yeah. Well, without overlap, you can fit 2 4-inch wafers on here if they have flaps.
Yeah.
Is that not possible at TMI?
No, they've got a smaller plate. This is 8-inch, right?
Yeah.
They've got a 6-inch.
Okay. Do you have a picture?
I might have it.
Okay.
Maybe like 7 to 100 nano. And
Okay.
Same thing for silica, but there is extreme circumstances where we've done this project close to a micron.
Okay.
But at a very like reasonable rate for one standard system.
Yeah. So my thing for basically for gold, that's how much gold are you planning to deposit? That's the main catch.
It really just depends on the project. But I typically do 50 and 100.
Okay. Those are reasonable.
What's an unreasonable amount?
Anything over 100, people need to ask me first.
Okay.
I think I said anything over 90, I need to be told about in advance. And the reason is, if you do over 100 nanometers, your name goes on a spreadsheet and you get a bill at the end of the month. Because basically, if people are doing small amounts of gold, we can subsidize that.
Yeah.
Anything, once we start getting to 100, 150 nanometers, that's a lot of money, man.
No, that's very understandable.
Yeah.
And we're built at other labs as well for abilities.
Yeah. And so basically, if you're planning to repeatedly, like consistently do like 100 plus nanometers, my advice is generally to bring your own source. That is the easiest way to just keep the tool functional for everyone. If it's just a one-off thing every now and then, just let me know and we'll add it to the tab at the end of the month. For reference, the rate we're using right now is 2.5 grams per 100 nanometers. So 100 nanometers get charged for 2.5 grams of gold, whatever the price of gold is at the time. Right now it's around $130 a gram.
Oh, I know it's $5,000 a month missing when I did that whole audit. It was for those gold purchases that weren't showing up.
Yeah, tell me about it.
It's adding up now. All right.
Yeah, Dr. Lee's gonna get another PO for about $6,000 or $7,000 soon.
I think that's a picture.
Oh, okay, excellent.
So this is the 6-inch plate at Central that we cut out and put into the system. We've made another one that fits 4 2-inch wafers here. But just like this is what it is, just for example. Like
Sure.
This is aluminum, aluminum frame.
So which is the aluminum?
That's aluminum there.
The square?
That's the wafer, and then this is the steel plate.
Okay, gotcha.
And we could probably make the steel plate.
Yeah. Yeah, whatever the weight of the carrier wafer is, maybe try and stay within a factor of 2. Again, I cannot promise that will work, but that would, I think, give a favorable chance of it working. Are you just using chrome as an adhesion layer? Yeah. Okay. And the aluminum?
Alumina, we're using...
Oh, aluminum, AL203, okay.
Yeah.
Okay, how much, okay, so you said, how much AL203 you think?
Typically we do 30 nano, right? 30 to 50?
Sure, not a problem. Same with the silica. So I'm not as picky about anything that's not gold. I mean, like, where's my, like $250, SiO2.
Okay.
I don't care overly much about this as long as the source doesn't get nuked. If the source gets nuked, then I'm gonna get annoyed because I'll have to just go in and replace it.
Yeah.
I would say, like, for just as a courtesy for other materials, like, if it's going over 200 nanometers, let me know. Just because, like, it's not gonna necessarily mess up the tool, but dumping that much oxide into the, or dumping that much of any material into the chamber can just, it can make it a bit finicky for the next person. So it's just, I want to keep tabs on it. That's basically all it is. So the load lock, this is the vacuum system we have. This is a touch screen. Do be careful with that. If you touch the cryo pump, it will turn the cryo pump off, and then it takes about a day to regen it. This is the cryo pump. Okay. Actually, really, you just don't need to touch. Okay. All the stuff you need is on the recipes on the right. Load lock's just trying to get down to E-6. It should be there. It usually doesn't take this long, so maybe the load lock got left open. The load lock gets left in atmosphere, it's just going to accumulate moisture. It's going to take longer for the next person to pump down. If the load lock gets left open overnight, it could easily take like 30 to 40 minutes for it to get pumped down. So just whenever we're done, pump the load lock back down. I tell people, like, you don't have to wait for it to hit high back or -6. Just start the recipe and then you can walk away. Just remember to start the recipe. But yeah, so definitely for something like a micron, I'd want to know in advance. Yeah, you can just DM me on Slack. Okay. So this is our aluminum oxide source. It's pretty easy to deposit from. It'll build up powder on the edges just because you have sidewall deposition. Silicon oxide. Yeah, so this one's, the pellets just come a bit larger, so it's not as clean of a, it's not as smooth of a deposition, but it still works really well. So the one thing with depositing the oxides, so we're depositing stuff like gold and platinum in the same chamber as SiO2 and Al2O3. So, sorry. LL pump is done, so we're just gonna, I don't know, we can hit close, doesn't matter. And then we want to get the sample from the load lock into the main chamber. We're gonna use the sample load recipe. Gold doesn't adhere to oxide. Oxides don't adhere to gold. So, since this is primarily a metal depth tool, the onus is going to be on the people depositing the oxides. When you put down an oxide, before doing so, just put down like 10 nanometers of chrome or titanium on the chamber before doing the oxide. And then similarly, just put down 10 nanometers of chrome or titanium on the chamber after doing the oxide. This is just to prevent the oxide from just flaking off everywhere and messing up the chamber. I think, do I have this written down? If I don't, I will.
I don't remember seeing it.
I'm sorry, come again?
No, he's trying to make sure what to put down before and after the...
Chrome or titanium is best. Those are just common adhesion layers, right? Titanium should always be in the chamber along with gold. So the oxides currently aren't in the chamber. If we want to use them, we'll have to vent the chamber and then pump it back down. I'm not going to... So the instructions are on the SOP for how to do that. I'm not going to do it today because Jatin, the user after me, I remember he needs the chamber to be at high back for his process. So, or like really like ultra high back. So right now, I don't necessarily believe that the chamber is at 2e to the -8, but the pressure probably is in the -8 range. It takes the chamber about 20 minutes to pump down from atmosphere to -6. It's going to take about an extra hour to get it down to -7, and probably like an extra 12 hours to get down to -8. If you have to vent the chamber to change out the source, then, you know, that's what you got to do. That's fine. But I just, best practice is to, you know, try not to vent it if we don't need to. Okay, so let's go to the deposition tab now. Over here, we have the source setup. This hypothetically shows what materials are in the tool. I say hypothetically because if you change out one of the sources, you have to go into here and, you know, change the source setup. People don't always do this. They usually do this, but sometimes people mess up. If they mess up, I want to know.
Are all the materials on that list, have they been calibrated with tooling factors already? Or?
Absolutely. Wait, which list? Like here?
Oh yeah, that big drop down.
In fact, most of the materials on this list aren't even like...
Options, okay.
Yeah. I have the tooling factors to the best of my knowledge. So these are the ones I'm like confident in.
Okay.
This is my, like, sort of scratch notes.
So those are work in progress on it?
Yeah. Or at least stuff like... it's stuff that I've done it once or twice, but there's a few materials like indium, vanadium, or like at some point someone was interested in depositing it, but it didn't really go anywhere, so I may have done like one calibration run on it, but I'm not going to put time into calibrating material that people aren't using. So, yeah. Stuff here is stuff that I'm pretty confident on. When a source changes, the deposition rates can change a little bit. Like if I have to have a new crucible, the tooling factor could change a little bit, but these are going to be pretty damn close. And if you do a deposition and realize that the thickness is more than a little bit off from where it's supposed to be, let me know. I will update this. But yeah, so just as a sanity check, like 95+% of the time, honestly, probably closer to like 98% of the time, this is going to be completely correct. Learn what the metals look like. Titanium does not look like chrome. Chrome does not look like nickel. And these powers here, like if you look in the logbook, you can see what powers people have been depositing these metals at. If you are, for instance, noticing that your titanium, which normally, 2.8 per, well, that's, I don't know why I did it that slowly, but, okay, Scott did 4%, about 0.4 angstroms per second. If you're at 4% and the titanium isn't doing anything, might be something up with that. This shouldn't happen. If it does happen, I'm probably going to start pulling people's access because it's supposed to, like, be better. But just fair warning that, you know, that is a mistake people can make. Anyways, so let's say we want to deposit titanium. Here's our source setup. Titanium is in pocket 5. Right now, we are on pocket 2. So we're going to go over here, set that to 5 and hit enter. When I hit enter, you'll see that the command got logged in the console. That also just verifies to you that the command went through. If you don't hit enter, it's not going to go through. So like with this tooling factor, if I change it to like 9 and then click elsewhere, you'll see it just goes right back. Okay, so we're on pocket 5. Now, we're going to go to the data sheet here. I am aware some of these are incomplete. That is just because they have not behaved completely consistently yet. When in doubt, use the logbook. So for SiO2, okay, so here's Peruta. He said 50 nanometers, 1.5%, 0.5 angstroms per second. There you go. It's really hard for me to like keep up with cataloging the behavior of everything. I'll do my best, but when in doubt, just look at what people have done recently. SiO2 can be a little tricky just because people don't deposit it quite as often, but you should still be able to find something. Yeah. So, titanium is on the data sheet here. The tooling factor is going to be 240. So, there's two crystals in the chamber. The sources are down here. First crystal's about here. Second crystal's about here. Your source is like here. The top crystal is the one that matters. The bottom one does not matter. The bottom one is dead. I do not bother replacing it because it was causing problems and the depth rate it gives is useless. This corresponds to the bottom crystal, this corresponds to the top. If you don't remember which is which, just change both of them. The bottom one is completely irrelevant, so, you know, go nuts. So, tooling factor for titanium is 240, so So I'm just gonna change both of these to 240 with just the addendum that this is the one that actually matters. From there, we're going to go to power control, turn on the power. If you're not logged in, the power will not turn on. If you are, sometimes it will take a minute from the time you log in to the time when it like realizes you've logged in. So just like, if the light's on, power doesn't turn on. If the light's off, the power will turn on. If the light's off and the power still doesn't turn on, then it probably means that there's something shorting the copper lines in the chamber. That's actually pretty easy to fix. You just have to vent the chamber and vacuum the lines. Hopefully you won't have to do it. You probably will at some point. It's easy. So we have a ramp rate and a set point. What do we think happens if we change the set point while the ramp rate is at 0?
Nothing?
Yeah, you'd
Is there
wish.
nothing, or you just jump to that?
Yeah, it's the second one.
What was the second one?
It will jump.
Okay.
So we do not want that. With something like titanium that's pretty sturdy, has low set points, it's not the end of the world. If you do something, if you jump the power on something like aluminum, you could very easily shatter the crucible. So we're always gonna set the ramp rate first. For titanium, the ramp rate I'm gonna have is 0.05.
Set ramp rate first.
And then we're gonna hit enter. And just verify that now that I click off, it's staying at 0.05. First set point, the first soak value is gonna be at 2%. So we're gonna go to 2%, and then we're just gonna wait for it to, you know, ramp up. Since we have a minute, are there any questions so far? Copper. Other than that, TBD, kind of. So these are all the materials that people have used or are using. Anything sitting out here is allowed. There's a couple materials that I have sitting in the back that are not allowed. Well, not allowed or allowed with an asterisk. So molybdenum oxide and antimony are not allowed. The reason being that when you try to deposit them, you will get depth rates of like multiple nanometers per second at very, very low powers. So you're not getting a controlled evaporation, you're just spraying the material everywhere. Niobium and tungsten are allowed, but with an asterisk, because those are, I don't know if you've worked with those metals before. So they're refractory metals. Really, really high melting point, low vapor pressure. You need a lot of power, a lot of heat to actually get those to evaporate. Very easy to burn a sample if you're doing that. Also relatively easy to overheat the cryo pump. So we're at 2%. And at this point, we should be able, vaguely. So the mirror's unfortunately a little scratched up, so it's a little blurry. But if you open this shutter, there's a mirror here and a mirror here. Crucible's down here. If you look sort of diagonally down, you should be able to see like an orange spot. Go ahead and just take turns until you've all been able to find it.
Okay.
Good?
Oh, yep, I saw the orange spot.
Nice. So diagonally down. Yeah. Found it?
That's fun. I haven't done metals in like 8 years. I'm ready. Oh, I had this job previously. I have 10 years of industry experience, which is shocking for someone my age.
Okay. So when we're at the first set point, we're generally going to want to wait for like maybe about 2 to 3 minutes. Basically, we don't want there to be dark spots left on the metal. We want to give it time to heat up uniformly. So
So like if the beam is out of the crucible, can we like
Yes, so it should generally be fine. This stick is going to control the center of the beam. This is going to control the size of the beam. So, up increases it vertically, down decreases it vertically, right increases horizontally, left decreases horizontally. And you can see, like if you move it, this little cartoon raster will move. Define accurate.
It shows where is the beam should go.
Relatively. I mean, it's a cartoon, right?
What's the square and what's the circle?
The circle is the crucible. The square is the rough beam sleeve.
And why don't we have that centered? Is there a reason we made that choice?
Yeah, it's because the crucibles over rotate.
Okay.
So the crucible isn't centered in the heart. So if we look at it now, I don't see any dark spots on the material. So we're gonna go ahead and ramp it up to 3%. You can also see we're starting to get a marginal dep rate. When it's that low, I don't entirely trust it, or at least I wouldn't start depositing, because it's very likely that's partially just kind of noise.
And why did you choose 3? Is that written down somewhere, or are you just slowly incrementing? Okay, perfect.
Yep. So 3%, so the second set point, I'm usually trying to target a dep rate of about 0.1 to 0.2 angstroms per second. That is not the rate you have to deposit at, it's just like a good starting point. You can see it's not doing that yet, but
like
that's
is
just
is it the time between set point 1 and set point 2 like 5 minutes or
no, it should be closer to like 2 or 3. It should.
like how long you have to wait?
I would say closer to 2 or 3 minutes. Really, you just want to wait until there aren't any more dark spots on the metal. Because once the metal's heated up, like, you can move on. So you can see dep rate's starting to climb a little bit. We're gonna just sort of wait until it's at around 0.1, which it looks like it almost is. And the reason I'm doing this is just because any dep rate below like 0.1 angstroms per second is not necessarily fake, but it's low enough that I'm not gonna trust the accuracy too much. So at this point, okay. So at this point, it's reached about 0.1. So we could start I think it'd be fair to start depositing now. So we're gonna open the substrate shutter. That's gonna let the metal actually land on the substrate. We're gonna hit accumulate. That's gonna cause it to start integrating this deposition rate. And you see how when I do that, this garbage pops up? Yeah, so we're just gonna hit reset to get rid of that. The exact order you press these buttons in doesn't really matter. You're just gonna want to do it like in rapid succession. Okay, so if we say we're trying to deposit, I don't know, 10 nanometers, obviously this deposition rate is a little slow. At this point, what we're gonna do is essentially just incrementally bump up the power. So I'm gonna go maybe 3.5, and this is where the logbook comes in. So you can see, okay, people have done 3.1, 4.0, 4.
Do you scratch out values that are where someone messed up?
No, these are values that changed.
Oh yeah, so yeah, I didn't know.
This?
Oh yeah, like the logbook. So are all those good values I can trust, or are there some botched versions in there?
They should be trustworthy.
Okay.
If someone does something that I don't like, I will generally make a note.
Okay.
Like if they said like, oh, I was depositing gold at 25% at like 5 angstroms per second, then
You'll
yeah, I'll I probably won't scratch it out. I'll just like circle it and write "don't do this."
Okay.
Okay, so now we're getting about 0.2. We'll give it a second for the rate to catch up, because the dep rate's gonna lag the power a bit, right? As it sits at a specific power for a while, that dep rate's generally gonna increase a little bit. So we'll sort of give it a second to see where it ends up.
And what's our uniformity across our entire substrate?
So that is not, okay, that's not something I have directly characterized. Physically speaking, the crucible should be centered under the wafer, and the process should be rotationally symmetric.
Okay.
So the center, I mean, if you just think about the distance from the crucible to the substrate, the center is going to be a little closer, so you might have marginally higher dep rates in the center than you would at the edges.
Okay.
But that is not something that has presented itself as an issue in the time that I've been on the tool.
Okay.
So we're at 3.5. It looks like it's stabilizing around 0.2. So we can try kicking it up to 4%. Titanium, you're generally going to do between 3 and 4%. Chrome, let's look at chrome. What have people done? So 1.5%, half an angstrom per second. 1%, 0.2 angstroms per second. 1.2, they got 6.5%. Or, sorry, 1.2%, they got 0.65 angstroms per second. 1.6%, 0.6 angstroms per second. The reason that value is sort of floating a bit is, unlike a lot of the other metals, okay, also we're at 4%, you can see we're, yeah, about 0.4 angstroms per second. We'll probably only deposit 5 nanometers just because we're not actually depositing on anything, so it's just a waste of time to go all the way to 10. So, once we are at 5 nanometers, we close the substrate shutter, tell it to stop accumulating, and then we're going to ramp back down. You don't have to stop at the set points on the way down, but we're not just going to cut the power. We are going to let it ramp back down. So what I was saying about chrome, if you've worked with chrome before, you'll know it doesn't melt down. It doesn't congeal the way the others do.
It sublimates.
Yep. So it's going to stay as those pellets or chunks similar to SiO2, which means if you deposit, or if someone deposits a lot of chrome, you can start drilling a hole in the middle. It's a really easy fix. You just take the source out and break up the chrome and smooth it out. But as the sort of surface geometry of the chrome changes, the dep rate's going to change. Generally, the more it's the less smooth it is, the worse the dep rate's going to be. And then, yeah. The good news, though, chrome is cheap. You can't really mess it up. Even if you do drill a hole in the chrome, like I said, you just break it apart and fill it in. So you don't have to worry too much. Whatever the most recent values in the logbook say, generally good. So once the set point's at 0, once the current is at 0, the amps, we can turn off the power. And then if we wanted to do another metal, we'd go ahead and switch the pocket. So if we wanted to do gold, we'd switch to pocket 6, and then tooling factor for gold is 120, so we'd set that. And then, you know, same thing as last time, turn on the power, set the ramp rate, go to the set point. If you're done depositing, then we're instead going to just run the sample unload recipe to recall the wafer from the main chamber to the load lock. And then, I mean, we're going to wait for that, but after that, you know, just vet the load lock and pump it back down. Do you have any questions while we wait?
What's the crystal size? Is it the same as
No.
No, it's not. So, for some reason or another, we have special crucibles. These have to be custom ordered. Like, the size is not. It's not one of the like standards. So we have a setup with, or we've been buying crucibles from IA Materials. They've made all of these for us. If you need a crucible, I can get you a quote. Do you think you need a crucible? Okay. Okay. Yeah, if you decide you want to do that, oh yeah, that's aluminum. So this is what aluminum does.
Oh yeah, you had mentioned that.
Aluminum's really good at wetting the crucible, and it has a really high coefficient of thermal expansion. So it'll melt, it'll wet the crucible, then it'll freeze, contract, and
Right.
yeah. The crucible the aluminum's in right now is an intermetallic. It's going to be one like this. You can see it is cracked along the bottom, but it's basically intact and stable, so it's usable. This is about as good as an aluminum crucible is ever going to look. That's one of the metals you really just have to be careful about shocking the power on, because so the aluminum crucible does this if you use like a slow ramp rate. If you just like shock the power, I would not be surprised if it just shattered. Okay. So the sample's unloaded, and as I said, we're just gonna run a little vent. How often do you usually do your depositions?
I probably do a deposition like once or twice a week.
Gotcha.
We've been using Texas State in this way, and of course the CDKs do it as well.
Are they functional right now? Well, the CNC is functional. I guess they are functional right now. I know they've been down for a while. Oh well. So load block is vented. I'm gonna go ahead and open this up. Again, just as a reminder, this door is solid metal. It's heavy. And then here we go. I think the last material that was deposited was chrome. We deposited 5 nanometers of titanium. It's not going to look different. If the last material on here was gold, you might be able to notice, but 5 nanometers is pretty small. So we'll take the sample out, just leave it on a clean wipe, and then we're gonna pump the load lock back down. So once the recipe starts, you are free to leave. Don't have to sit around and wait for it to pump down all the way. If the next user is like at the tool waiting for you to finish, you don't have to pump the load lock down. If the next user is not at the tool and you don't pump the load lock down, then you accept responsibility for whatever happens afterwards. So if they show up in a couple minutes, I'll talk about this in a second. If they show up a couple minutes afterwards and load their sample, everything's fine. If they don't, and it takes the next user 20 minutes to load their sample, not fine. I just suggest just pumping it down. What is this? So, the short answer, this does not matter. This is completely irrelevant. But we have a bunch of air in the load block, right? And then all of a sudden, so the pressure gauge is gonna be right here. So all of a sudden the valve gets opened, we start pulling vacuum. There's just gonna be a brief pressure spike where the pressure the gauge reads is gonna be over 1,000 torr. All it is saying is that it can't read over 1,000 torr, So that value it's showing, when it's showing 1,000, it's just saying like, hey, that's not the real value, this is just the max I can read. Generally speaking, this will show up for like a second or two and then stop. We just hit acknowledge and it goes away. If the message doesn't stop, like if it's just continuously showing up, and that would mean that the pressure isn't dropping at all. If you see that the pressure just is not dropping at all, it probably means the load lock is just open and you're trying to pull vacuum on atmosphere. But, you know, if you run into an issue, just let me know. I generally try to get to it. I mean, if I'm at lab, I'll try to get to it within like 30 minutes. If I'm not at lab, I'll try to get to it within the day, or I'll talk to someone who's able to fix it and get them to get it sorted out.
So like, if we have to vent the chamber,
Yeah.
So when we put down, like how much can
Yeah.
we start the
So
process?
you've got so the short answer is you just run the PC pump recipe, and whenever it completes, you're good to go. More specifically, it's gonna get below -5. So 9.9 E-6 is the first like acceptable value that it'll let you deposit at. Occasionally, if the chamber's been open for a while, or this happens with people if they put like a lot of tape to hold their substrate onto the carrier wafer, the load lock or main chamber will not pump down in the time allotted by the recipe. If this happens, it'll like throw an error and say like PC pump aborted, yada yada yada. Just run the recipe again. If it doesn't work the first time, just run it the second time. If it doesn't work the second time, then let me know, because it really should be working the first and second time. And yeah, you can see like this time, I think it took like 8 minutes to pump down last time. This time it's taking about 5. If it's pumping, if the load lock's empty, it should take about 4 to 5 minutes to pump down. Any questions?